Hello everyone. Today we are doing section 10.2 Fourier series. And actually I got a new helper. It's going to be my cat. Well, let's start. So what are Fourier series and why do we need one more series? Well guys, you probably remember from linear algebra that if we have a set of vectors which are orthogonal, you can actually use it as a basis to represent any other vector in that space. Well, let me remind you, if we deal with 3D space like X, Y, Z, right? And we do have vectors I, J, and K, which are making this orthogonal set means that I is orthogonal to J and orthogonal to K. They all three are orthogonal to each other, so the dot product between them is equal to 0. Well, if we do have set of vectors like this, then we can take any arbitrary vector, something like vector A, and represent it through these three vectors and like some coefficients. Basically, guys, we do a projection of this vector on vector I and J and K. How do we do a projection? Well, to do a projection of like vector A on vector I, for example, we are sorry, not supposed to be the line here. Sorry, what we can do, ax coordinate, for example, it's going to be a dot product between vector A and vector I, right? And for all other coordinates, y coordinate, it's vector A, dot product vector J. I hope you still remember a little bit of linear algebra and vector A and vector K, right? So if you use AX, AY, and AZ, you can use them as coefficients to describe your vector. And that's usually what we do, right? When we say that something in 3D space has coordinates 1, 2, 3, we mean actually this 1, 2, and 3. AY is J and AZ is K. So usually no one is writing down even I, J, K, they're just writing the coordinates, right? AX, AY, and AZ. And usually they're going to look like this. 1, 2, 3. Means that the endpoint here is like 1 unit on the x-axis, 2 units on the y-axis, and 3 units on the z-axis. You find the point, and that's going to be the end of the vector. That's how we represent vector in orthogonal system. Well, we already know that some spaces can be like finite dimensional, like 3-dimensional, for example, 4-dimensional. Some spaces can have infinite dimensions. One of the spaces with infinite dimension is a function space, right? We already know about like Taylor series. Taylor series has a basis of vectors looking like this. 1, x, x squared, x cubed. These are series centered at 0, but we can actually do any other series centered not 0. And we can represent function f of x using this basis and multiplying the vectors of this basis. So these are vectors of this basis by like different coefficients, like for example, a0 multiplied by 1 plus a1 multiplied by x plus a2 multiplied by x squared, and so on. Well, we do have formulas for these coefficients, actually, how to calculate them, but well, generally speaking, that's going to be also similar representation. It's just like coefficients a0, a1, and a2 are going to sit over here, but the vector is not going to be like three-dimensional. It's going to be like infinitely many dimensions. Okay, so Taylor series. What other series we have? During 19th century, people developed lots of different series. When they realized that it's very convenient to use series to represent functions, they developed like maybe hundreds of different series. Well, so far we do know Taylor series, but today we are going to learn another series, Fourier series. What are Fourier series and how people are using them? Some functions, some functions f of x are not necessarily like exponential or x squared, or some functions are like sine and cosine series, like not sine and cosine, like periodic functions. when we do have periodic functions, makes sense to use series with period, or like something with the same period which can represent, which can work as a basis. Well, again, periodic functions kind of work better together with periodic series. It does not mean that Taylor series is not going to represent sine of x. It will represent sine of x, but not that good, let's say. It will represent it nearby the point, but not like almost everywhere. But if you want to deal with some periodic functions, other series are going to work better. I'm going to introduce you this series, and we are going to talk a little bit about if they are orthogonal and how to kind of calculate these coefficients, right? For vectors, we know that they are dot products, actually. The coefficients are produced by dot products, but for other series, for example, we do know that for Taylor series, we have a special formula, right? For example, for coefficient A2, it's going to be what? A second derivative of x, of f of x at the point, in our case at 0, right? Divided by 2 factorial, right? That's a special formula. What are going to be the formulas for a different series? Give me a second. I want to maybe scroll it up. Oh, sorry, instead of scrolling up, I'm just drawing on my whiteboard. There is supposed to be a way to move this whiteboard, right? Yeah, doesn't want to move actually. Okay. Well, I think maybe I should just erase it. I totally forgot how to use this Zoom whiteboard because my pen did not work for a while with Zoom whiteboard. So it was like a little bit hard for me. What is this actually? Maybe that's going to produce a new page for me. Yeah, page 2 actually, very good. Right, so I'm going to introduce a Fourier series. Let me change the color. Let's make it Fourier series. Well, Fourier series are going to be periodic series, and they're going to look like this. A0 over 2 plus sigma am, that's going to be the coefficient, which we are going to use, cosine of m, doesn't look like m, actually looks too many legs, cosine of m pi x divided over L plus b m sine of m pi x divided over L, and here is going to be from m equals 1 to infinity. Well, again, what is this? That's infinite series. We use sigma notation to not write down every term, but actually what is changing in this sigma notation? Index m. So for m equals 1, we are going to have a1 cosine of 1 pi x over L and b1 sine of 1 pi x over L. What is L here? L is going to be half of the period. For right now, let's just kind of remember this formula, which we're going to use a little bit later. For right now, I want to kind of maybe work a little bit with these functions, but I don't want to really integrate them because it's going to be like not easy. So I'm going to calculate a period of one of this like sine or cosine function. And then we are going to move to orthogonality. You see, it's just a set of functions. Before we had powers, now we have sine, cosine, different periods. I'm going to calculate and show what are the periods, and a free coefficient, like normally in like Taylor series 2, right? So I'm going to do the cosine. Remember that t is called a fundamental period. If it's the smallest number for which f of t plus t is exactly equal to f of t. Smallest number. Small. Well, for sine and cosine, we do know that the smallest number which repeats sine and cosine is actually what? 2 pi, right? Because we are dealing with same sine cosine here, I'm just going to consider sine. So imagine that cosine of m pi over L x plus some period equals cosine of m pi over L just x without period, like I'm using the formula, right? I'm going to open this parenthesis, and we're just going to calculate period right away. X over L plus I'm kind of multiplying the common factor by everything equals, well, if we want to make sure that cosine of like one angle alpha, for example, is equal to cosine of angle alpha plus something, this something must be 2 pi, the smallest one for which it's going to work. So, which is going to set up for us equation m pi t over L equals 2 pi. Okay. And, well, just let's cancel pi. And the period is going to be 2L over m. Well, guys, if m equals 1 for the very first cosine function, the period is going to be just 2L. So basically 2L is a period of like the smallest period of cosine function. And that's going to be actually a period of the function which we are going to use for representation, or for which we are going to look for representation. The series is a discrete way to represent actually a function in a Fourier series. We also have Fourier integral, which is going to be continuous way to make a Fourier transform. Maybe like after we deal with series, I'm going to show you the integral too. It's going to look very much like Laplace, just a different kernel. Okay, now we do know the period of the series of each term, right? Depending on m, it's going to be like 2L, 2L over 2, 2L over 3, and so on. Now, what I'm going to do, guys, I'm going to show that Fourier series are orthogonal. What I'm going to do for this, I'm going to kind of prove it for one special case. Let me, is it allowing me to do another page? Oh, page 3. Okay, different color. So I'm going to use a special case when 2L equals 2 pi. Why? Because it's going to be easier for me to integrate. But it's not going to kind of change anything about like generally about the series. So let me kind of write down how the series is going to look if I set up 2L equals 2 pi. So the series is going to look still A0 over 2 and plus sigma m equals 1 to infinity a m cosine. And we do remember that we had if I do 2 pi, it's not gonna, well, I actually wanted to make L. Yeah, L is equal to pi, right? Sorry. I thought I should substitute 2 pi into my like formula. So remember the formula was mx, the formula was m pi x over L, right? If I substitute pi instead of L, if I put over here pi, I'm going to cancel the pi and I'm just going to have mx. Well, again, it's not going to make the series very different. That's just like going to be a particular case when 2L equals 2 pi. All the rules we develop here are going to work for any L. So let me then erase this and no, I don't want to clear. I'm just going to write down mx here, sorry. Draw. So mx plus bm sine of mx. Well, it just like it's going to give me shorter expressions. It's not going to make anything else easier. Well, guys, in this series, we are going to introduce a dot product as an integral. So dot product between two vectors here is going to be integral from negative L to L. And it's going to be like, for example, sine of pi mx over L by sine of pi nx over L dx. Well, that's just like dot product between two vectors. I'm going to write it down like v1, v2 dot product. If you have like one of the vectors is sine and another one is sine. Because my L is equal to pi, I set it up to pi, right? I'm going to convert it into minus pi to pi sine of pi x by sine, oh, sorry, missing m. Let me put it back. Okay, m pi x sine of n pi x. Well, again, we are trying to find a dot product between two vectors. Vector with index m and vector with index n. Maybe I should put like indexes here so it's going to look like more what I multiply m here and n here. So I'm kind of multiplying my two basis vectors. Well, what I'm trying to say that I'm trying to prove that they are orthogonal. What means orthogonal? Vectors, two vectors are orthogonal if the dot product is equal to 0. And if you multiply a vector by itself, it's supposed to give you like something like 1, right? That's what I'm going to prove. So right now, m and n are not equal to each other. And I'm going to use a formula to do this integral. And the formula, you probably remember, sine formula, which was looking like this. Sine of alpha by sine multiplication by sine of beta equals 1/2. We do this formula in calculus 5b when we do integrals, equals cosine of alpha minus beta minus cosine of alpha plus beta. I'm going to use this formula and kind of modify this expression, okay? Formula from trigonometry. Doesn't look like I'm writing down formula. I'm writing down something unclear. Yeah, cat does not approve it. Well, let's use the formula, right? We do have the argument here is m pi x and pi x, and I'm just going to put it under the integral. I'm going to put 1 over 2 outside of the integral. I'm going to copy my limits minus pi and pi. And again, we can prove all the same stuff if you put L instead of it. It's just going to be just a little bit easier to see, actually. Well, he left the building. That was not good. Okay, guys, I'm sorry, but we'll need to kind of turn him off, I guess, right? Give me a second, because he decided to leave us. Does not give me actually. Okay, so we're going to. Okay, he decided to move actually. In a different place, more comfortable. Let's continue working with our integrals. So we do have two cosines. I'm going to write them down. So that's cosine of alpha minus beta. Well, here alpha and beta are basically same, just m and n are different. So I'm going to write down m minus n. And it's going to be pi x, right? Minus cosine of m plus n and also pi x. And then dx, right? I do need one more parenthesis here, like to show that dx is multiplied by both of them, right? Well, I think maybe I will maybe integrate one of these cosines. I don't want to integrate both of them. Let me do the integral of this cosine to show you a special rule which we're going to have. So I'm going to just take the integral of cosine of m plus n pi x dx and show you what is going to happen. I don't think that is going to fit here, but okay. Well, integral of cosine is what? That's a sine of m plus n, right? Pi x, and we'll need to divide by m plus n pi over here. Well, just because that's a coefficient of x, right? And kind of need to do substitution from minus pi to pi. Well, let's look at sine. What is going to happen to sine? We know that m and n are natural numbers, and they actually start with 1. So the smallest one of them is 1. So for example, we can have 1 plus 1, or 1 plus 2, or 2 plus 3, but that's going to be a natural number. Why do I write down pi here? Pi is already canceled. I'm sorry, guys. I did wrong. When I canceled L, I forgot to eliminate pi. There was supposed to be no pi, of course. Here. Where is the extra pi? Here is extra pi unnecessary, and here is extra pi unnecessary. Here is extra pi necessary. I already canceled it with my L equals pi. And I just forgot. Yeah, I think he does not want to be recorded. But the only thing I understand. Okay, I think we are going to say him goodbye. He's distracting me actually from teaching the lecture. So let me turn him off. Wow, he's seeking something. Good guy. Okay, but we're going to kind of stop using. So here, well, one more pi. Sorry, did I have this one? There is no pi. Well, it's very nice that we can erase something just by clicking on it. Do I have any more pi? No more pi. Okay, so what is going to be m plus m? It's going to be a natural number, right? If instead of x I put pi, I'm going to have 5 pi, for example. I know that sine of pi, 5 pi, 2 pi, 3 pi, 4 pi minus pi is equal to 0. And minus pi is going to give me like sine of minus 5 pi. It's also equal to 0. So this integral will be just equal to 0. What is going to happen to this integral? Well, for this integral, we have little complication. Complication is going to happen when m is equal to n. Here, it does not matter, actually. But here, because it's going to go in denominator when you write down the answer, it matters. So we're going to assume that m is not equal to n first. Well, what is going to happen? Well, we're going to have pretty much the same answer. Just instead of plus, we are going to have minus here and minus here. Maybe, it's not allowing me to scroll it up, but I want to kind of write down maybe like the answer right over here. So the answer is going to be sine of m minus n x over m minus n. If m is not equal to n, everything is clear here. And if I plug in pi here and negative pi here, well, difference of two natural numbers is going to be like either natural number or integer, but that's going to be like, okay, 2 minus 3, for example, that's minus 1, but minus 1 pi is still going to be 0. So all of these are going to be zeros too when I do substitution of minus pi and pi. The only one which I did not consider yet was the case when m is equal to n, right? What is going to happen when m is equal to n? When m is equal to n, I'm going to get a 0 here, right? And if, I'm going to write it down, if m equals to n, then this term is becoming like cosine of 0, which is equal to 1. And my integral is going to look like this, integral from negative pi to pi, 1/2 1 dx. Well, which is kind of easy to integrate, right? 1 over 2, and that's going to give me just x from negative pi to pi, right? And I guess I don't miss anything, right? No, everything is correct. Okay, I do substitution, and I'm going to get 1 over 2 pi minus negative pi, which is going to give me like 2 pi over 2, which is going to give me pi. Well, ideally, guys, I want to have 1 here, but pi is not bad too, right? All all dot products between signs are going to be equal to 0 for different m and n. And the only one dot product is going to be equal to a number pi. And this dot product is going to be the dot product of Vn by Vn. Maybe I should summarize it on the next page. So the only dot product Vn by Vn is going to be equal to pi. All other dot products Vm by Vn going to be equal to 0 if m is not equal to n. Well, what is good that actually cosines are going to have a same pattern. So if you multiply two cosines, use the same formula, you're going to get the same answer. And if you multiply sine and cosine together, there is a formula too, and that's going to bring us also to all zeros. Well, what does it mean? It means that the system is orthogonal. Orthogonal means that dot product between the vectors of the system are going to be zeros, except vector is multiplied by itself. Normally, guys, we want to have unit vectors to be our basis. Here are not unit vectors. Unit vectors are going to give me 1, right? If I multiply I by j, for example, I'm going to get 0, but I by I is going to give me 1. But well, that's not bad. I mean, we are going to adjust it, and just kind of we can always set up that integral is going to be not equal to, like, our dot product is not equal just integral, but integral divided over pi. If we do this, then pi is going to disappear. Okay. Now I'm going to just write down a general formula, and give me a second. I'll stop it for a second and move to a different place. Okay, now we do know that these cosines and sines are orthogonal. How to find the coefficients? Well, how to find this AM and BM? What I'm going to do, guys, I'm going to multiply both sides of this series. Imagine that the function is already represented. We just don't know the numbers for AM and BM. So what I'm going to do, I'm going to multiply my function by cosine of mx on both sides and integrate. I'm going to take the integral f of x by cosine of mx from negative pi to pi dx. And on this side, well, sorry, I supposed to first like write down the term. It's gonna be a 0 over 2 by cosine of mx. I should probably use a different, I'm going to use a different letter instead of m here, otherwise it's not going to be clear like what is the difference between m and n, okay? So I'm going to use a different letter, plus an, n from 1 to infinity, cosine of nx plus bn sine of nx, and again multiplied by cosine of mx, and there here dx, and there here the integral. Now remember that all these sines and cosines are orthogonal. What does it mean? If you multiply these two and integrate them, you are going to get 0 in all the cases when the function is not exactly itself. For example, this cosine multiplied by all the sines is going to give me just a bunch of zeros. Cosine mx multiplied by cosine of nx is going to give me a bunch of zeros too, except for n, which is equal to m, right? Remember, when function is multiplied by itself, it's going to give me non-zero. Well, why don't I kind of write it down? So integral from negative pi to pi f of x cosine of mx dx. And on this side, I'm just going to have integral. Well, if n is equal to m, I'm going to just use m as my coefficient, am. Because cosine is going to be multiplied with the same index, I'm going to write down cosine square of mx, just this one by this one, right? And dx from negative pi to pi. Well, am is a constant here, right? So we can always take it outside. I'm just going to calculate the integral of cosine of mx dx. Well, I kind of don't remember, guys. If you still remember, like what are the how they to calculate the integrals, but I remember we had something like a double angle formula here. Constant is outside already. We just need to do the integral of cosine square, right? Double angle formula was looking like this: 1 plus cosine of 2 mx divided over 2. For cosine square, it was 1 plus cosine square, and then dx here, right? So I'm going to kind of use this formula. Well, I'm almost done with calculations. I'm going to start solving problems just like in a minute. So I have 1 over 2 plus cosine 2 mx over 2 dx. Well, I don't have space again, and I have to move to a different page. Instead of doing this, guys, we already did the integration, right? If we integrate cosine, we are going to get a sine divided by 2m, right? Everything. But because that's a natural number, multiplied by 2, it's still a natural number. When I plug in minus pi and pi, it's going to be the sine of like 2 pi or 3 pi or minus 3 pi, which is going to be 0. So the only part which is going to stay, maybe I should write down this integral again and write down that the integral will be 0. Again, why does it happen? Because we are dealing with periodic function and kind of just we are doing one period of this, or like many periods depending on them, of course. Okay, now what is going to be this integral? This integral is just going to be 1/2 dx, right? And well, I don't have space. I'm going to continue over here, am. So it's going to be pi plus pi. I'm plugging in into x divided over 2, which is going to give me am pi. So now I got a general formula. Let me kind of add a page and change my color. So my general formula is going to be like this: integral from negative pi to pi f of x. That does not look like pi. F of x cosine of mx dx equals so what I got, well, 2 pi divided over 2 is pi, right? And I got pi by am, from where my coefficient am equals 1 over pi from negative pi to pi of x cosine of mx dx. So I just got the rule. To calculate the coefficient, I'll need to integrate my function multiplied by cosine and kind of plug in the limits, and that's going to give me a number. Guys, I don't want to do a similar integral for sine. For sine, everything is same. You multiply the whole expression by sine of mx. You're going to see that almost all integrals are zeros because the system is orthogonal, except one integral, which is going to be actually like the coefficient of the same sign by which you multiplied. So I'm going to just write down the coefficient bm, okay? And well, you kind of, because you are going to do the same steps, of course, the formula is going to look similar. So it's going to be f x sine of mx dx. That's how we calculate the coefficients. For a0, it's going to be a little bit different. What is going to be a0? I'm going to do a0 separately. Well, you've probably seen that formula a little bit weird about a0. It's a0 divided over 2y. Well, let's see. So what do we have like on the kind of, what is the function which corresponds to this? Well, if these are cosine, if this is sine, a0 is actually multiplied just by 1, right? So the function which corresponds is just like 1. So I'm going to have f of x multiplied by 1 dx from negative pi to pi. And it's supposed to be equal integral of a0 over 2 well, also multiplied by 1. I'm going to do write down 1 over here from negative pi to pi. Well, I'm going to do this integral and then write down like what is going to be a0. So I have 1 over 2 a0 and pi plus pi here, right? It's just like dx is going to give me just x. This is a constant. You can take it outside. And what I'm going to get actually a0 pi, from where the formula for a0 is 1 over pi integral from negative pi to pi f of x. Well, you can write down multiplied by 1 dx, but no one is doing this. You see, guys, if we don't have in our series, which is on one of the previous pages, a over 2, this a over 2, then the formula for a0 is going to be different from our formulas over here. Here, it's the same formula, actually. You just see, here we multiplied by cosine, here we multiplied by sine, and here we multiplied by 1. Not just. You can treat 1 as a cosine of 0x, okay? And the formula is same. If you don't have this 1 over 2, the formula, it's not going to be same because you are going to kind of divide over 2 by, and that's just like, you know, not divide, multiply by 2. So we kind of have the formulas now. Why don't we try to solve something? Use it on some function. I'm going to start with considering function with period of 2 pi. So we just can use directly our formulas. But then I'll consider 1 or 2 functions which are going to have a different period. So let me move to a different page. So, and change the color again. Okay, I don't know, let's do this blue. So I'm going to consider a periodic function. Example 1 is going to be equal to 0 from minus pi to 0. And it's going to jump to 1. Basic, very basic example. And this is going to be equal to 1 until next pi. And then we'll go back to 0 and kind of repeat this. Just a rectangular signal. Lark, right? Here's going to be my x, and here is going to be my f of x. That's my function. The period of my function, the period is going to be equal to pi. And I'm going to start with calculating coefficients. I do have the formulas for them already, right? So my a0 equals 1 over pi integral from negative pi to pi of my function f of x, right? dx. Well, I do know what is my function f of x. I know that from negative pi to 0 is equal to 0. And from 0 to pi is equal to 1. So I'm just going to plug it in. And because I already kind of know that integral of 0 is 0, I'm going to just integrate from 0 to pi. 1 dx. Which is going to give me integral of 1 is going to be what? Just x. Substitution of 0 and pi. Well, 0 is going to give me 0, pi is going to give me pi, and my final answer is 1 over here. Okay. am 1 over pi integral from negative pi to pi. More complicated. Well, guys, I'm not gonna, maybe I should write down the formula once. The cosine of mx dx. And because my function is equal to 1 only from 0 to pi, my integral from minus pi to 0 is going to be equal to 0. So I'm splitting, I'm going to write it down. Integral from minus pi to 0 plus integral from 0 to pi. This one is equal to 0. This one we are calculating. So it's 1 over pi integral from 0 to pi. And then the function, because the function is equal to 1, it's just 1 cosine of mx dx, which is going to be equal 1 over pi. The integral of cosine is what? Sine of mx divided over m. Don't forget, if you differentiate sine, you're going to get cosine multiplied by m. So you will need to use it from 0 to pi. Well, 0 is going to give us 0, right? Pi is going to give us sine of pi m, which is 0. So we are going to get 0. All of these coefficients are going to be 0 because it does not matter what is m, it's still going to be pi, 1 pi or 2 pi or 3 pi or whatever, right? What I did, actually, we're gonna move to next one. Maybe I should move over here, guys. How about BM? BM is coefficient of the sine. I'm going to copy it. Guys, I'm not going to write down integral from negative pi to pi. I'm just going to just plug in the function, okay? So that's 1 and sine of x from 0 to pi. We already did it like 2 times. I think everyone can understand it. So which is going to be what? Minus cosine of mx divided over m divided over pi from the front from 0 to pi, right? No, we're going to substitute. Here we are going to get something because cosine of pi or cosine of 0 are not equal to 0. At 0 is 1, at pi is -1. What I'm going to do, I think I'm probably going to take this minus and pi m outside. I'm going to write down as a separate fraction, pi m. And I'm going to just do the substitution in cosine. So I'm going to have a cosine of pi m. I'm plugging in pi instead of x and 0 instead of x, right? Minus cosine, if I plug in 0, it's cosine of 0. This one is equal to 1, right? This one is going to be either equal to 1 when m is even, 2 pi, 3 pi, 4 pi, or equal to -1 when m is odd. What is going to happen when it equals to 1? We are going to have 1 minus 1, which is 0. So 0 m even. If you have -1, we're going -1 minus 1, which is going to give me like -2. So I'm going to have like -1 over pi m by -2. I'm going to write down m odd. Odd means like 1, 3, and so on. Even it's like 2, something like this, right? So minus and minus are going to cancel, and I'm going to get 2 pi m, and I'll need to write down that m odd. Well, guys, sometimes you just can give it as an answer. Everyone knows what are odd numbers. It's 1, 3, and so on, right? Sometimes you can write it down like from natural numbers. I'm going to show you both ways. I'm going to accept any. Either you can say in words it's odd, or you can write down a formula. But generally speaking, you know, as you like. So what I'm going to do, I'm going to first write down the answer and kind of just write down that m is odd. And the second, so a0 equals 1, right? Formula has a0 over 2. So I'm going to have 1 over 2 plus, I'm going to write down sigma. I'm going to have only sine terms, right? Cosine terms are going to have 0 coefficients. So I'm going to have my term is equal to over pi m sine of, sorry, not supposed to be pi here. It's supposed to be actually m here. M x m from 1 to infinity, and I'm going to write down m odd. Well, in some books, they're not going to write down m odd. They're going to give a formula for m. Odd numbers can be described as 2n minus 1. Here, n is any number. Like if n is equal to 1, we're going to have 2 minus 1 is 1, right? If n is equal to 2, it's 2 by 2, which is like 4 minus 1 is 3. So n here is 1, 2, 3, all numbers. Well, I don't know if it's a better way to do it, but for me, it's going to be same. But this is alternative way to write it down, and I'm going to kind of write it down in an alternative way. So in the book, if you see it, you understand it. Sigma 2 over pi. Instead of m, I'm going to write down 2n minus 1. By the way, you can write down 2n plus 1 and then start with 0. And from 1 to infinity, sine of 2n minus 1 multiplied by x. Oh, now this thing is interfering. I'm going to move this. Okay. I'm just going to write it on like over here. sorry, n equals 2n minus 1, n equals 1, 2, 3, and so on, natural numbers. Okay, so that's how the answer can look. And again, not very clear what is this. Is it n or it's pi? It's supposed to be n, of course, but 2n minus 1. Okay, so that's what it's supposed to be like, and that's my final answer. Okay, I want to take 2 minutes break before I move to my next function. And I think we're already like too far. You know, guys, I think I can do my next function maybe, maybe just on my examples. I'm going to start it and just show you like the rest of the solution in my notes, okay? Because the lecture is becoming very long. Okay, so let me choose one more page. So let's consider a problem. What if period is not equal to pi? Well, let's just consider a function f of x equals 1, negative 1, sorry, for x from negative 1 to 0 and 1 to minus 1 and 1 from 0 to 1. I'm going to draw the picture and you're going to see that the period is like period equals 2. It's going to be like minus 1 and that's 1 here. It's x and that's like y. So the function is doing something like this. And kind of repeating it. So period is equal to 2. How should we deal with this? Well, we are just going to kind of change the coefficient in front of our x, right? So instead of sine of sine of mx, we'll write down sine of m pi x over L. So we're kind of changing our x to pi x over L. What is going to happen if we do this? Well, here L is going to be kind of the distance or kind of half of the period, like t over 2, half of the period, of actual period. What is going to happen here? For example, guys, just let me explain why we have this. It's very easy to understand. Imagine that x here is equal to like 1. X here equals to 1. L, in our case, because my period is 2, is going to be also 1. So we are going to have like 1 over 1. So it's going to be again m pi, and that's going to kind of have a same period, like from 0 to 2 pi. We're kind of scaling x to change from 0 to pi if it's not really changing from 0 to pi. So here x can change from negative 1 to 1, but like the whole thing is going to change from negative pi to pi. And well, it's going to have the same rules, right? How it's going to affect my formulas? Let me write down the formulas. And well, maybe I should just calculate the period here. I don't think that my explanation was enough. So let's calculate sine of m pi x over L plus t is going to be equal to sine of m pi x over L plus m pi t over L, and that's supposed to be like 2 pi. So we are going to have m pi t over L equals like 2 pi, from where the period is, well, we need to cancel pi here and here. So pi is going to disappear, and we are going to have t 2 over ml. Well, we remember that the period of actual function is like 2 pi over m, right? So here, the period, if m is equal 1, the period is 2l. So that's going to tell us like that that's what we actually set up, right? So how the general formulas are going to look? Well, let me kind of give you general formulas. Imagine that we have a function which kind of goes from negative L to L, and that's one period of a function. Function can look anyway like this, for example. So that's just like the period is equal to L, and the function changes from negative L. Let's kind of make it dark, and then over here can be anything, can be something like this. It's not necessarily supposed to be continuous function. Just the period is 2L. So the formulas are going to look like this. Well, it's 1 over L from negative L to L. Guess what if you look at what I did, I just put instead of pi L everywhere. It was 1 over pi, now it's 1 over L. And the period, the limits of integration were from negative pi to pi, now from negative L to L. Maybe this way it's going to be more understandable. Cosine of pi m max over L dx and bm. If you kind of understand how it works with pi, I think it's not going to be a problem to move to a different constant L, because, well, consider that pi is L and that's it. Sine of pi m x over L dx. So these are new formulas. I'm going to call them general formulas. And we just can use them to do our calculations. Well, maybe I should solve one more problem on the board, but no more than one, okay? Okay, so for the function I had on the board, my L was equal to 1, right? Because the period was equal to 2 over 2 was equal to 1, right? L was equal to 1. So my A0 equals 1 over 1 here, right? Remember 1 over L, from negative 1 to 1, f of x dx. Well, if your L equals to 1, you just kind of don't write it. It's okay. And what we have, the function is equal minus 1 from 0. So two integrals, minus 1 to 0, it's minus 1 dx, right? And the function from 0 to 1 is 1 dx. So just like minus 1 dx, it's going to be minus 1x, right? From negative 1 to 0, plus 1 by x from 0 to 1. You don't need to write down x's. I'm doing this to explain a little bit better. Okay, what we have? Well, 0 here is going to give me 0, minus is going to give me plus, but because the formula, Newton-Leibniz formula has minus, I'm going to have a minus. Then over here, I have 1. It's going to give me 1 minus 0. Plus 1. Okay, equals to 0, so no A0. AM. 1 over 1, integral from negative 1 to 1. And I have again my function f of x multiplied by cosine of m pi x, and my L is equal to 1, right? Well, I'm writing down it once, but normally I guess you can skip it. If your L is equal to 1, okay, just don't write it. Okay, so what I have again, two integrals, right? Integral from minus 1 to 0 of 1 cosine of pi m x dx plus integral from 0 to 1, sorry, minus 1, right? 1 cosine of pi mx dx. Well, the integral of cosine is what? Sine of pi mx over pi m, write the coefficient a minus because there was a minus, substitution of -1 and 0. This one is going to be the very same integral, just pi mx over pi m and substitution of 0 and 1. Well, here 0 is going to give me 0. 1 is also going to give me 0 just because it's sine of pi m, natural number. So this one is 0. And this one is going to be also 0. So my coefficients in front of cosine are all zeros, but sometimes. Well, now I'm moving to coefficients of sine, bm. Guys, I'm going to write down the integral right away, okay? I'm kind of tired of copying everything 10 times. So we have -1 by sine of pi mx dx plus integral from 0 to 1 of sine of pi mx dx. So what we have a cosine of pi mx over pi m. Derivative of cosine is minus sine, so this minus goes into here into cosine. Here we're going to have minus because there is no minus, and I'm going to just copy cosine of pi m x over pi m. Substitution here, -1 and 0. And substitution here is 0 and 1. Okay, so 0 here is going to give me 1 over pi m. Or maybe I should keep 1 over pi m, like separately. 0 is going to give me 1. -1 is going to give me cosine of minus pi m. And we know that for even m, it's going to be equal to 1. For odd m, it's going to be equal to like -1. So I'm going to write down minus plus -1 and plus even minus odd. Well, when it equals to plus, we are going to have 1 minus 1, right? 0. When it equals to minus, we are going to have minus, minus, and they combine together. So it's going to give us 2 odd m for this one. Minus, well, at 1, same story, either plus -1. Plus -1 plus even minus, and at 0 is 1 minus 1, right? So what we have? Well, plus 1 minus 1. So even is going to disappear. Odd is going to give me 2 minuses. Equals -2 odd m. Now I have 2 minus -2. So I'm going to get just 4 m odd. Well, I should not write down equal odd. But okay. What about pi m? These are my coefficients. So I'm going to just maybe write down the series. I'm thinking maybe I did a mistake with this 4, but okay, guys, if you see a mistake, well, fix it yourself. You know how to deal with these integrals. If I start checking it, it's going to make my video even longer. So I'm just going to write down the answer, okay? So my function f of x, unfortunately, which is piecewise defined, right, is going to look like a0 is equal to 0, I think. Only sign coefficients are going to stay, right? So I'm going to write down sigma m from 1 to infinity, and the coefficient is 4 over pi m sine of pi m x. And I'm going to write down odd, okay? I'm going to convert it into a general formula. Okay, so what we see, if you look back at our function, let me return back at our function. No, not here. The function. You see that the function is actually odd. The symmetry is around the origin. The function is odd, and we represent it through odd function. Well, which is normal, right? Odd function, the property, like if you change from plus to minus, like your argument, if my representation is even, it's not going to change anything, but my odd function is going to change it to minus. So that's like very logical to have odd function represented through the odd functions and even function represented through the even functions. Well, there are some functions which are neither odd nor even. They are going to have both sine and cosine, but generally, if your function is even, it's going to have only cosines. If your function is odd, it's going to have only sines. Okay, well, what I think, I'm going to stop at this point. I'm already so tired and my cat is trying to escape the room. Okay, guys, just try to do more integrals and check this one. Maybe it's not 4, maybe it's 2, maybe I'm missing 2 somewhere. Don't look like, but who knows? Okay, so let me